One last example for class 23. Here is problem 685 from Borgnacki. A piston cylinder contains 0.1 kilograms of water at 500 degrees Celsius, 1000 kilopascals. The piston has a stop at half of the original volume, similar to this figure right here. You should notice that this figure is for a different problem, and this is not ammonia, and it is not 20 degrees. The water now cools, right? So it's gonna cool. So the piston has, yeah, okay. So it's gonna start out in this position right here. They're gonna cool it down until it gets to be 75 degrees Celsius, and the outside temperature is 25 degrees Celsius, not 20 as shown on to this previous problem. You'll notice there's a different problem number. So we want to find the heat transfer and the entropy generation. Anytime you see these kinds of stops, just be aware that you're probably in for like a two-step type of thing. So on like a oh no, let's go PV diagram because that'll make a lot more sense, I think. So you're going to come up here and so you're going to have like a constant pressure, right? Because it has this heavy thing. It's the image, there's the word problem, but there's also the experience of what you had with other problems. Anytime they show this kind of thing, this thing has a weight, right? They don't show any external force on it. So it's all about the weight of the thing and the area. With that weight in that area, it's going to be a constant pressure. It's going to be a constant pressure until it gets to these stops, right? When this thing gets down to there, they're going to keep on removing heat from this. I don't know what that was. Supposed to be an arrow. That's sad. That's like a really sad arrow. And then more heat is going to be then it's going to be constant volume, so it's going to come down right there. So that's part of reading a problem and looking at it, is to recognize that that's going to be something along those lines. Constant pressure till it hits a stop, then constant volume. So let's go and do this problem. So first thing I'm going to do is get some properties. I think 500 degrees Celsius, 1000 kPa. I think you get a good chance it's going to be superheated. So let's check that out. And from table B.1.3, we look it up, and pressure at 1000 kilopascals and T at 500 degrees Celsius, and sure enough, it is superheated, so we're in the right place. We find out what the volume is going to be, or the specific volume, 0.35411 cubic meters per kilogram. We also going to get the internal energy. I got a mouse in my roof, not my roof, in my ceiling, and I am going to go Tom and Jerry on that son of a bitch pretty soon. It's making noise like all day as I've been here, and I am going to go nuts. So what I'm thinking of doing is I'm going to get like a syringe and some mouse stuff, and I'm going to poke it through the drywall. Although I could put it through the lamp. There's the overhead lamp. Probably I got little gaps and stuff in there, and I could stick it through in there. That's what I'm going to do. I'm killing it. I'm killing it. I'm sorry if that's like cruel, but I can't get them out any other way. Do I need the mass? I was given the mass, so it doesn't matter. I don't need the mass. 0.1 kilograms. I just wrote that in a random spot right there. I do know what V2 is going to be. That's V1 over 2. Genius. And I don't need to write that out. It's going to be 0.177055. All right, so as I mentioned, and maybe drawing these things out can really help you think your way through the process. PV, get up there, and we're up here in a superheated regime. We have a constant pressure. I come down here, boom, right there. And so let's label this 1. Let's label this A, and then label that 2. Right? We could have gone 1, 2, 3 if we wanted to, but let's decide to stick with what they did in the book. Okay, I'm just being honest. So we want to get to this spot right here, find out what the properties are at that spot, and in particular, find out what the first thing to do is figure out what the quality is going to be at that spot, and get all the other variables that we want. So we want to go to A, right? So this was like 1 up above. Now let's go to A, and that's going to be and I'll go. You know, we're in the mix region, so we go table, and we have a pressure. We know what the pressure is going to be just right at there, right? Where it's still the same pressure when it hits these stops. It's going to be B.1.2, and at P is equal to 1,000 kPa. Do we need the temperature? I don't know. What's the saturation temperature? 179.9 degrees Celsius. If you had to draw it on a TS diagram, you would probably want that too. So I don't know. We can also, so we take a look at F and 0.001123 kilograms, and then I'll put VG in there. I don't really need VG, but I'm in part of this discussion. I do 0.19444 cubic meters per kilogram, and we can see that this right here is in between the two. So we've confirmed that we didn't make it all the way over here, or that we are somewhere in between there. Like we could have stopped like right there. So we weren't quite sure that it was in underneath the dome, but now we know for sure because at this pressure, our volume right here lands in between there. So we also need the VFG as part of that, and that's 0.19332 kilograms. So we go ahead and put it in. V is equal to VF plus X, let's call it XA, VFG. And I don't have to plug these numbers in for you, right? So this guy goes into here, that goes into there, that goes into there. We can find XA. We do that, and we end up getting 0.91004. So it's 91%, so that's a lot. All right, but now while we're here, let's go ahead and get UA and SA. All right, so we'll take, and I'm not going to write out the equations right here all the way through because I'm getting tired, but we can find the UF and the UFG and use that XA, and we can find out what this value is, 2,419.7. If you can't do that, if I just lost you by that step, please come tell me. I'll do it for you. It's you and me. We'll walk through it. Anyway, so we got this midway point right here, and we're going to keep on going down. Now it's going to go to 75 degrees Celsius, but it's going to be at this same volume, right? Because we're going straight down. It's a constant volume process coming straight down to 75 degrees. So we're going to go to 2, and that's going to be at table B.1.1 at T2 equals 75 degrees Celsius. Notably that P sat, so the pressure has now been allowed to go down, is 38.58. So that's in a vacuum region, by the way. We're taking things out, enough heat out that we have created a vacuum inside this. And let's see if it's still a vapor mix. We can hope it's a vapor mix. It'd really be a mess with us if not. So we take a look at that location. VF is 0.001026. Okay, good news. It didn't become a liquid. I didn't think it would, but you didn't know. And here's VFG, because I don't have to write VG, but we know if it's below VFG, that it's also definitely below VG, 4.13021 cubic meters per kilogram. And what we can find from that, setting it equal to this volume right here, we end up finding that X2 is very small, but still in the mix. All right, so it's 0.4%, but that's okay. And then we can use the other values at there, all the F's and the FG's, and we can find U2 at that quality is going to be 406.016 kilojoules per kilogram. S2, 1.29955 kilojoules per kilogram degree Kelvin. And now we can go and say the conservation of energy is going to be U2 minus U1 equals Q1 to 2 minus work 1 to 2. And we know this is constant volume, right? So that's good news. So we get what this is going to be integral PD, let's call it V. We'll go M times that, right? And so we have M P V2 minus V1. And since it's cut in half, we could actually take a shortcut there if we wanted to. It's 0.1. Oops, sorry about that. 0.1. And the pressure during stage 1 was 1,000. So this is the constant. Okay, so one thing to note is the work between 1 and 2 is really the work between 1 and A, because there's no work that takes place between A and 2. So that's all we need is this work right there. So we get the specific volume, and really we could just, because it's 1/2 of the thing, we could just multiply it if we're lazy and I really feeling lazy, so I'm going to do it right there, right? Because that's the delta V, right? That's the delta V is 1/2 of the thing, and so we end up with. And if you look at the actually, I feel bad now. I'm gonna have to. I'm backtracking, right? This is V2. V1, remember, was double it, right? So I'm doing this so you can see the signs. I messed up. I feel bad now, but I won't feel bad for long because I'm gonna go to bed soon. So this ends up being negative 17.71 kilojoules. Negative. Whoa, all right, okay, cool. So that must be there was work in, right? Work out should have been positive right there. And then we also, so if we go back up into here, we can go, and I could rearrange this. I guess I'll rearrange it. Q1 to 2 is going to be equal to U2 minus U1. Actually, I should recognize that I already have that U's as lowercase u's. So I'll go M times U2 minus U1, and then plus work 1 to 2. And so we go 0.1 kilogram, and U2 was 406.116. That's a lot of numbers. Minus U1 all the way back at the top. That's a lot. So 3124.34. So that's like it definitely can be negative. And then plus the negative 17.17. So Q1 to 2 is negative 289.5 kilojoules. And this is one of the things we wanted to find. They also wanted to know the entropy generation. So this is equation 637, rewritten around a little bit. And so we would find that S1 to 2 gen is going to be equal to M times S2 minus S1 minus Q 1 to 2 over temperature. But mind you, that's going to be a negative Q, so be on the lookout. 0.1 times our S, which was 2, which is 1.29955 minus S1, which was 7.7621. You can know, oh no, we're going to get a negative S10, but here's the negative, and there's the negative 289.5, and we need to divide it by the temperature all across, which it's in a room of 25 degrees, so that comes out to, what is that, 298? 298. And so, running off the page, S gen 1 to 2. I'm getting tired of that 1 to 2 thing. I keep forgetting to put it in there. Is 0.325 kilojoules per degree Kelvin. Boom. And there you go. So we are we have a positive value, right? So it's important to note the signs on how they're working out through here to keep track of them. So I think we got that going for us, which is nice. And now we've got enough videos to sink a ship. See you in class on Tuesday. The end is near.